Today I'm going to talk on the topic which is I started recently because of the green thing, right? Walking. And Hong Kong is a very walkable city. And actually, this project was started about 4 years ago when our chief executive say Hong Kong has to be the most walkable city in the world. And then asked for people to submit proposal. So I submitted one proposal. We call this a strategic public policy research proposal. So it was funded. So I started look into what we can do better for Hong Kong. Those who have been to Hong Kong know that Hong Kong walk a lot, people. Because driving and private vehicle is not very common. And public transport, you always have to do the last mile and first mile walking connection. So we do walk quite a bit. So the question is, how can we further improve that? So people can enjoy walking even more. Framework of this study is basically, we start out the vision. Walking means different things to different people. If you think about elderly, think about physically challenged, they mean very different things. So the first thing we want to look at is what is that, what is a vision for certain districts. So we deliberately chose 2 districts. One is very old, a lot of seniors. One is a lot of footbridges in the area. So we want to look and compare how people perceive the 2 areas in terms of walking or walkability. And then the next thing we did was to build a network platform. Walking paths are very complicated. You can imagine a vehicular path just, is very easy. People don't care about the pavement. People don't care about security, street lighting, climate, air conditioning, even to the width of the sidewalk. So there are a lot of factors that we have to code in the network, and also 3-dimensional. People walk under tunnel and walk through shopping centers in Hong Kong. So it's a pretty complicated network that we have to code. And the next is do behavioral modeling. How do people choose between different paths? Sometimes we often find out distance is not a very good measure. People think about air conditioning, think about, do I walk by a green area? Do I care about shopping? Do I care about connection to public transport? So there are a lot of factors affecting their behavior. And finally, we do some policy analysis. If we were to improve in the neighborhood and area, should I do this or that? Which is more cost effective? So eventually we build a tool to help the government decide on infrastructure investment for improving walking experience. So that is basically the project. So the first thing we did was to talk to the stakeholders. That part is quite laborious because you have different groups of people. The elderly have different objectives, people with disabilities, commuters, visitors. So we have to find out what exactly are they looking for when they think about choosing a particular path to walk. And then we have to think about the government side. They control the infrastructure, what kind of building codes they have, planning guidelines, and so on. So understand the suppliers, the provision side, why they don't do it. Are there obstacles that prevent them from doing a better job? And on this district council is more like the neighborhood people, stakeholders that voice out for a certain perspective, like they want to improve public transport, they want to make the neighborhood more walkable. Those are basically local politicians, you know what I mean? District councillors. Those people are connected to business, connected to various stakeholders. So we have to do a lot of this kind of stakeholder engagement to find out the compromise or the objective of different districts. Now, this part is very labor intensive. So because we want to code the walking network in a 3-dimensional. So you can think about this are all 3D. So we have to find a very high resolution map first, and then there are 2 angles. One is start from the GIS angle of it. One is starting from the BIM, building information modeling, because there are a lot of shopping centers are actually part of the walking network. So this part, we spent a long time to simply code a network. Now, fortunately, the government then bought into this idea. they code the whole thing for Hong Kong now. So it's on the web, it's open access. For those who are doing walkability, you can use Hong Kong as example. The entire 3D walkable network is open access now. But when we started the project, we did a lot of work ourselves to demonstrate to the government that this is doable. Don't worry about it's the very detailed, very time consuming to say the least. So, and then so we did it to 2 districts. One's the Kwun Tong area. Kwun Tong is a very old neighborhood, mixed with a young, very new neighborhood. This is an uphill area, and there's an MTR station somewhere here. So you can see, want to look into this kind of neighborhood. Is it good for walking? And why? And we want to quantify it. You know, there are things like walk score, walkability index. They're very subjective, very loose to define areas walkable or not. We want to be very precise, very evidence-based, and I want to find out exactly what spot need to be improved. So we want to be very detailed and quantitative. And then this is Tsuen Wan is the area known to be a city of flyovers. So a lot of walking footbridges connecting the city. So also 2 layers. So 1 layer is footbridges, underneath layers of vehicular car traffic. Want to see the 2 different ways how people perceive and how do we improve. So those are 2 areas we focus on. In this talk, we look into this mostly. An old neighborhood. How do people perceive about their walkability? Now, this from the other angle, you can see that this is a BIM rendition of the network. You can see there are stairs, there are ramps, there are traffic crossings, and then very detailed. So we start with this level of detail, because you can even think about, for people, they don't follow this kind of grid walking, right? They walk diagonally across. So when you think about the walking network, the number of links is just tremendous. So we have to find a way to clean up the network so that it actually represents to a scale where we can manage. And when we do the discrete choice, we also have to develop a new set of things called recursive logic. Can I do link-based logic instead of the path-based logic? So that is, we spent a long time trying to make sure that our understanding logic model can work with this kind of detail. Give you a sense, like in Kwun Tong area, it's a very small area. We are talking about 50,000 links, and then tremendous amount of detail inside. So how do we make the computation achievable is a big thing here. And then eventually, those who do choice modeling would be familiar with this. So suppose I'm going from O to D. There are many paths. I just list out 3. Actually, easily hundreds of paths linking in OD pair, because people can walk anywhere without the restriction of the roadway. And then we think about also what attributes people would care about. So we broke it into 3 types: functional attributes, safety, security attributes, environmental, aesthetic attributes. Functional meaning, is the pavement good enough? Is the slope too steep? And so on. So we have to combine all this into the MLE to calibrate the coefficients. So that's what we set out. The set of attributes is actually very large. I'll talk about it in a moment. And then after we build a model, we calibrate the discrete choice model, and we look into network design problem. How do we intervene the roadway infrastructure, or the escalator is on a slope, or escalator infrastructure, so that we can improve the walkability of the area and so on. So we call this a policy modeling and stakeholder analysis. This tend to be very important. Now, in the old days, without this tool, people argue, the district councilors basically, if you win this kind of escalator, you go back to the voters, right? You win votes. Actually, the box size is very small. Even if you build 1 escalator, you're going to win next time. So there are a lot of those kind of fights to win for my district, to build a escalator here. without evidence. So it turns out to be those who get the biggest voice will get things done without talking about the benefit costs and so on. So what we hope to achieve is put things on the table, make it evidence-based. So let's not shout, let's look at the numbers and so on. So this turned out to be a very useful tool to get buy-in and to avoid unnecessary fights. So we begin with this thing. We coded a network that took a year, very detailed network. And then the first thing we look at is a stated preference approach. And then we look into the stated preference, we build a model, and then we we call this accessibility or utility-based accessibility measure. And then we want to use it to appraise new infrastructure projects. So that is sort of a step, kind of like traditional. Now, what is difficult is that there's so many parameters that people said they care about. They could be distance, one of them, signal timing, to have to walk across, and the signal is very bad, escalator, are there restaurants along the route, interchange, crowdiness, width, a lot of detail, weather protection, and so on. So we start with a big list, and then we eventually screen down a pre-survey, and then we screen down into the one highlighted in red here. So those are the factors that people felt they care about them in choosing their routes. And then once we nail this down, all of them need to be coded in the network because they need to be reflected in their choices. So again, it's very labor intensive to code all these attributes, much more than vehicular traffic. And then we go for the SP survey, the efficient design. So basically, it's a usual compare a pair and pick the one that the respondent prefer. We start out with 251 respondents and give them a pair. We highlight the difference under the sun, under cloudy day, with vegetation, green, without, and so on. So we create, each of the respondent will do 17 choice pair, until we feel that they are sufficient to help us to calibrate the panel mixed logic model. We start with 251. We send a paper out for review. The reviewer say, hey, 251 is not enough. And then we did another one over 1,000. So that one passed that. It's a lot of work. So it just work. When I think about it, just a lot of sweat. How do you talk to 1,000 respondents and then ask them to do 17 choice pair comparison? So it's a lot of work. But then the results are much more reliable. Now we know the SP, even though it's very, you can use a de-efficient design, the numbers are still not very reliable, I have to say. People don't tell you exactly what they would prefer to do. So if you think about this, so we create a measure called the sidewalk distance equivalent, meaning that if a 1 meter on the ground flat, nothing is 1, then with a restaurant, 1 meter, we have -63, meaning people would prefer. There's a restaurant there, their perception is shortened their walking distance by -63 meter. So having a restaurant, a store is very important. People walk by, something to look at, they don't feel like the distance so long. So it's negative, meaning is subtracting the walking distance. Green is good, street light is good, air conditioning is good, heavy traffic is bad, add to it, and so on. At gray, crossing is bad, and so on. So you look at this kind of sidewalk distance equivalent, it gives people a physical sense whether this attribute adds or subtract from the perceived distance. I thought this is a useful way to interpret the results. Now, this is SP. And then we find out SP is actually exaggerate the effect of that. So, but anyway, based on that, we can map out the shortest distance path So the two are the same area, one is shortest distance. This is a maximum utility. When we factor in the shops, the greenery, the air conditioning, and so on, you can see that actually people prefer to walk this longer path and not here, absent here, because there's a steep slope here. So people prefer to curve around and walk down instead of go straight down. So you can see that the two actually are quite different in terms of the perceived distance. You can see if you look carefully inside, people prefer to actually curve a bit more instead of walk straight down. You can see here's a very steep slope here. So this is a way where we capture the maximum utility path. Now, how do we define this accessibility measure? We use a log sum term to define it. We call utility-based walking accessibility. So from R to S, suppose there are 3 paths. Obviously, in reality, there are many more paths. So we simply take the log sum of all the possible paths linking R to S and take it to be the accessibility measure between the 2 points. The more paths you have, this will drop, okay? So it's a usual property of MEU is as the choices increases, the perceived utility will improve, okay? So so you can see, suppose there are 3 paths here, a -12, -13, -11. If you do the log sum of 3, it's actually shorter than the 3, the shortest of the 3, okay? Which is typical of the EMU kind of characteristics of other. So anyway, we adopt this as the measure of walking accessibility measure between 2 points. And then we expand later on into a region, multiple OD and so on. So in each of the OD pairs, we can do this. And then this will give you a sense of the heat map. So this is the MTL station right here. And then by applying this, we call it UBWA. And then you can see that the more blue is the color is further away, meaning the sidewalk equivalent distance increases. Now, it's not a concentric circle. It's influenced a lot by the infrastructure of this area here. So you can see this area is pretty bad. So by knowing that, one perhaps should not put a senior home in these areas. It's not very accessible. There are good areas around here. So help policy setting, what areas are good for what people. We didn't differentiate the age now. In the latest paper, we differentiate between age. Because different age perceive the network differently. Young people, they don't care about lift. But old people, they care a lot about escalator. They worry about this thing. So we actually, in the latest work we just finished, by even looking at this heat map across age, they look at the area very differently. Okay, how do we balance is an important question. Now, I just mentioned about SP is not very good. So we go into the RP. I'm going to spend a bit of time talking about this RP. Again, RP is even more work. So what we try to do is create walking accessibility measure. There were existing ones, mostly distance space, a little bit not very detailed accessibility measure, utility based, and there are some using this 5D or 4D paper, very important paper. I think developed by Severo and Cockerman some time ago. I think it's called 4D paper, and then they expand to 5D. So using macro way to characterize a neighborhood, whether it's walkable or not walkable. Now, what we want to do is actually create very detailed estimates for a neighborhood, including something called a barrier effect. Barrier effect would be like on a 2D map, you don't see that there's a cliff. In a 3D map, then you can see there's an escalator. So what we try to say is that let's capture the 3-dimensional of the network into it, so that something similarly to be very nearby actually is impossible. because there's an elevation difference in it. So we capture the 3D effect or the barrier effect into it. And then in this approach, we took into account the 3D network, the barrier effect, the walking attribute preference, like air conditioning, shops, and so on. And then we also, because of the size of the problem is so huge, we don't want to do choice set generation. We want to convert the whole problem into link base so that all the possibilities are captured without having us to predefine a set of root choices ahead of time. So we call this a link-based measure. And then finally, we use it to assess and appraise infrastructure improvement. Now, in RP survey, you can see that we use a concept called pedestrian following survey. So we follow, but then walk with them, basically. And all of it, walk with them, the GPS signals are all messed up, you know. Again, this is very labor intensive. It's only possible because we're very good students. So this is about 220 pedestrians. We follow them while asking them questions. We walk with them. So we track the path, and you can see that the paths are all over the place because pedestrians walk not along walkways. They walk across and so on, so various sorts of things. So the first thing we do is that we have to fix it by snap it back into the grid. So we use a hidden Markov model, map matching. So the idea is the following. Suppose there are 2 points in the GPS. They are not on the grid. They are somewhere outside of the grid point because of GPS error. So what we do is, suppose this is the path using 2 points. Suppose the first point here, the second point here, there are 2 possibilities. The pedestrian could have walked this way or could have walked this way. So we express the probability of the transition, okay, by using the difference here, map it to this point and map it to this point, and look into the transition probability of the 2 points. And then we maximize the likelihood of that. It's computationally very extensive because each dot, you have to compute this thing. And then eventually, the result is very nice. This is a GPS signal, we snap it back into the walkway. So this is the best we can do, is a maximum likelihood. Whether they're exactly on this path or not, we don't know. We just maximize the probability of snapping it back. So we did that for the entire set. So everything we snap it back into the grid. And now, because it's snapped back to the grid, and each of the grid link has attributes. Is it on a slope? Is it with air conditioning and so on? So we actually, each segment of them, we know the attribute of that segment, okay? So we can actually calculate the utility of each of the chosen paths, okay? Now, there comes this link base. Again, pedestrian can walk on many, many different paths. Some of those are between roadways, so you don't know which one will be taken. So we pre-select a set of routes, then this route set will be huge. Also, we may have create bias. So what we want to do is create this entirely from a link base. That means all the routes is captured through a link, and the link is exhaustive. And therefore, we don't have to pre-select any route within the set. And then we then calibrate using MNL. Again, this is very computationally heavy. So the idea is the following, just roughly, we are using some sort of dynamic programming approach. So suppose someone walk along this link and then to a path below. What we want to do is create a like dynamic programming. This node represents all the possible utility thereafter. And then when the people walk from here, they think about this link plus everything after. And then, or this link and thereafter. So what we do is collapse everything into a dynamic programming kind of structure. So without going too much into the mathematics, so the idea is like this. So we are again using a log sum term. So suppose you are here. So there are a lot of possibilities. So when you do the log sum of everything thereafter, okay? And if it's already at the destination is 0. And then we rearrange the equation. Now what we want to find out is the utility term aggregated at this point using log sum. So we will find every point with the log sum term defined, then the problem is solved. So how do we find the capital VDN? So this is basic definition of this. You do the log sum everything after, and then rearrange the equation. Now what we have after that is sort of like a fixed point. We get to this, this is the Vn, the node log sum value. So we have this linear equation here. So what we need to do is solve this very huge linear system. Once we solve the linear system, we know the value at each node, given the parameters. And then we go back to do the log likelihood to solve for the coefficient. It's a convoluted, but it's a doable. The map is very clean. I cannot explain it fully in here, but I think in the paper, we explain it fully. How do we convert otherwise a path-based logic choice into a link-based kind of formulation? And we do it like this. And then we can calibrate the coefficients for each attribute here. So sidewalk, stair, at grade, crossing, and so on. So this is what we did. Now, this set of parameters, when we calibrate, it's much more sensible as compared to the SP. The SP saying that a shop will be like minus 63. Now here, the scale become much more reasonable to me. So if the sidewalk distance is 1 meter of ground counted as 1, then the coefficient of footbridge is 2.9. So people would walk 2.9 meters to get rid of 1 meter of footbridge. So that's how you interpret that. It's sensible. It's about 3 meters. And then staircase higher. You have to climb, right? It's 5. At grade crossing is a bit higher. It's not as bad as staircase. Tunnel, people really hate it because security, perception, and so on. So even though it's not physically tough, but security and sense of, crime and so on. RAM is also not good. People avoid ramps, and so on. So this set of calibrated coefficient are much more believable, at least from a user's perspective. So, and then we apply that to find out the walking accessibility measure of using the recursive logic kind of results. The definition again, basically at each node, you look into all the possible paths that you can go from R to S, but expressed in the link form. So this link form captures all the possible paths linking an O to a D without pre-specifying what path is that, okay? I thought this is a very powerful way to capture the network using this recursive logic kind of formulation. So that is with no choice set generation, we don't have to pre-specify the choice set, and then and therefore it's also unbiased. So you can see the resolution much higher. So we make it like this is a Guntong case, very high resolution now. So we do a lot of POI, points of interest, within this area. And this is the MTR station 41. Again, the shapes are similar to the SP, but much more refined now. So you can imagine what is 3,000. This is saying that if you walk from here to there, the equivalent sidewalk distance 3,000 is about 3 km. Okay, and people in general would not walk that far. And there are good neighborhoods. This is a 250. In Hong Kong's MTR system is about 500. So you can see the catchment area of MTR is around here, like this. So this result is very useful to capture the catchment area of MTR station. Once you multiply by the population density, then you find the catchment population of this particular MTR station. Now, this is really the policy comes in, where there's a big debate. One district councilor say they want to build this thing in a very nearby neighborhood. This kind of like a escalator walk uphill. This is a slope, very steep slope. The other try to build this elevator here. Now they fight. So they want to win votes, right? So, and then they look similar, right? I don't know which one you prefer. One is escalator, one is a lift and go horizontal. So we apply this methodology to appraise these two infrastructure projects. We can even pinpoint who would benefit from it. So you can see that this is the original. This is with project one, with this thing. This is the thing here. So this is the same thing. So you can see, we can see where the blue area become yellow is an improvement. So you can see this area become yellow. And then this darker blue become lighter blue. So you can even pinpoint who would vote for you, because those are very tiny neighborhoods who would gain from this project. Infrastructure 2. So the change is not very substantial, right? So you can see here versus here. So the blue area is gone. And then a little bit of change here. But you can see here, this area improved quite a bit by this thing. Okay, so with this kind of tools, we can basically capture the benefit of that. Of course, here we don't differentiate between age or different types of needs. We can change a model into very easily into people with disability. So who would benefit people with a disability or wheelchair and so on. So we can do that. So that basically summarize the talk. We develop a link-based walking accessibility measure that incorporates street-level walking attributes. And then we develop a hidden Markov model to snap the GPS observations with error to the 3D maps so we can trace that. We also propose a concept called sidewalk equivalent. So we translate everything into on level ground, how far away, which is very easy to perceive, converting slopes and everything into level ground kind of distance, which we can interpret physically more easily. And we also use it to appraise 2 projects. Actually, who wins, I don't know. But at least we put all the numbers on the table and people can decide for themselves which one will benefit who more. So this is basically the talk. So let me stop here.